It is my pleasure to announce Professor Anton Kapustin from Caltech to today's Rocky Mountain Mathematical Physics Seminar. Professor Kapustin will speak about higher Berry classes for many-body quantum lattice systems. Please.
Thank you. Can you hear me? Yes, you can, right? All right. So here's my. So this talk is mostly based on a joint work with Nikita Sopenko, which came out in January. But I'll later give some more references, which sort of serve inspiration for this work. So the talk is about higher Berry phase, but first we're going to make a very brief review what Berry phase is in quantum mechanics, and then why it's not trivial to extend it to many-body systems, and then I'll change gears a little bit and discuss some technical results about lattice systems, in particular how to think about conservation laws on the lattice in a way which is similar to what we do in the continuum. So even though, we'll see that many of the things we do on the lattice have on the continuum have a parallel in the lattice. And after that, I'll go back to this high Berry phase and use its results to define high Berry phase or Weisel-Witten terms for lattice systems. So in standard quantum mechanics, with the that's for now, by standard, I'll just mean something really simple, like maybe a bunch of spins, finite number of spins, so you have a finite-dimensional Hilbert space. We have the following setup. Suppose you have some parameter space, which is really just some compact manifold, typically, and you have a fixed Hilbert space of finite dimension, and then you have a Hamiltonian, which depends on its parameters. So Hamiltonian is just a self-adjoint operator. Maybe it's a smooth family, so it's just a smooth Hermitian matrix, smooth matrix valued function on M. Now, and for simplicity, let's assume that the lowest eigenvalue of this matrix is non-degenerate. So it has a corresponding eigenspace has dimension 1. It doesn't have to be this way, but for generalizations to many-body system, that's the most natural starting point. So, okay, so I have this eigenspace of dimension 1, whose eigenvalue is, the smallest eigenvalue of this Hamiltonian. And as you vary the parameters, well, you always get this eigenspace. You get a line bundle, which is called the line bundle of ground states. Now, this line bundle is I don't know how to do with this, so it's not in the way. Okay, somebody's saying that some problem with slides.
Can you resume share? We cannot see the slides, just the first page. Oh yeah, that's good. Thank you. Yeah. You're muted now, Anton.
Okay. Sorry. Okay. So I have this family of lines over manifold M, and moreover, you have this setup. You also have a canonical connection, this line bundle. That's called the Berry connection. That's fairly recent realization due to Michael Berry. And then connection has curvature, which is a closed 2 form. And the way I define things is actually purely imaginary, so put I here. And it's well known that if the curvature of any connection on a line bundle it defines a cohomology class, so the RAM cohomology class, which is an integral class, like in the if you divide by 2 pi I, it's an integral class. It lies in the image of the usual map from integral cohomology to de Rham cohomology. And moreover, this class depends on the line bound, not on the Hamiltonian. So that's class I'll call the Berry class. So what's the meaning of this? Well, if this class is non-zero, it means that your family of Hamiltonians cannot be deformed to a sort of constant family without this eigenspace of ground states colliding with some other eigenspace. So it's a topologically non-trivial family of Hamiltonians, or in reality, we know that the line bundle has a Chern class. I actually don't need to know in the Hamiltonian. Just knowing the ground state, the family of ground states already allows you to extract this cohomology class. So basically the point is that there are like, topologically non-trivial families of ground states, which come in the corresponding family of Hamiltonians can also be called topologically non-trivial. So the question is there something similar for many-body quantum systems? Well, let's see. Now, so what do I mean by that? Well, I mean that there is some lattice, well, say hypercubic lattice in Euclidean space. And one big difference in this situation is it's an infinite system. So Hilbert space is actually not specified at the outset. The basic object is not the Hilbert space, but rather the algebra of observables, which I call this curly A here. And it's a product of matrix algebra. So every side of the lattice contributes a tensor factor, which is a matrix algebra of some size. Actually, I think it is a finite-dimensional C-star algebra. They take tensor product. Well, more precisely, take tensor product and then complete to get a C-star algebra. And well, how to get to Hilbert space? Well, it's a bit non-trivial. So first of all, you define time evolution on this algebra of observables using usually Hamiltonian. I'm not going to specify for now what this means. And then you look at ground state of that Hamiltonian. I'm going to say later what this means exactly. But again, one can say this without using the Hilbert space. And then that ground state is some positive linear function on the algebra of observables, invariant under time evolution. It just follows from definition of what the ground state is. And after you have that, only then you can define the Hilbert space using this Gelfand-Nymark-Siegel construction. Okay, so this standard, that's actually standard. This complicated procedure is actually standard way to treat lattice systems and thermodynamical limit, in infinite volume limit. So the trouble, if you try to apply it to a family of Hamiltonians on a fixed algebra, then there's a problem because in general, the Hilbert spaces you get are, well, let's see. They're not naturally isomorphic, and in fact represent, for every state you get some way for this observables to act on this Hilbert space, but the corresponding representation of the algebra A are not naturally isomorphic in general. So you don't get actually a fixed Hilbert space in a natural sense. Let's see. What's going on here? Okay. Now, it seems like some sort of mathematical complication which has no relevance to physics, but actually it's physically, it's also significant. So to see, well, so, but if you think about from physics viewpoint, it suggests that maybe, well, there should be some generalization nevertheless. And that generalization, okay, a bit subtle. So if you think about parameters as degrees of freedom, which you can like make them varying in space and time, then also these phi's local coordinates become themselves function space and time, then you can reinterpret this Berry connection, corresponding one form, in the following way, using the language of field theory. So we would say, well, if you have a gap system with an energy gap, because you sort of integrate out all the excited states, you're only left with your ground state. But that gives, if you ask now, well, suppose you treat your parameters themselves as fields and allow them to be varying in time, say. if you're dealing with a zero-dimensional system, that you only can depend on time. Well, then we can ask, what is the effective action? Get, and the lowest term in the effective action has this form. It just has a first derivatives of phi. And that whatever multiplies it can be thought as a one form on the parameter space. More precisely, it's a pullback of the one form of the parameter space, where this map phi from the time coordinate, a time real line to the parameter space. Now, if you look closely, this so-called one form is not really a one form; it's a connection one form. It's defined only locally in the parameter space. And what's well defined globally is this connection, the Berry connection D plus A. Okay. And what I mean by it's defined locally, well, it's if you cover with charts, you get one forms, but as you go from chart to chart, this one forms differ. Well, don't glue exactly, but they may differ by exact terms. What's well defined though is a curvature. Well, the D of A, because that's glues into honest two form. Now, if you think about this, so this AB is the Berry connection and FB is the Berry curvature. But if you think about it this way, then there is it's obvious how to generalize it to higher dimensions, because if you'll say in higher dimensions, I would say D spatial dimension and D plus one space-time dimensions, the corresponding effective action term will depend on parameters which can be now functions of space and time. And if this would write something like this, the natural analog Berry term is the pullback of some D plus one form on the parameter space. Now, this D plus one form is only D plus one form locally. Again, as you go from chart to chart, it might change by exact things. Now exact means D of some one form. And moreover, these one forms themselves must satisfy, well, one can show that they should satisfy some compatibility condition for this whole thing to be well defined. So say on triple overlaps, it should be, this sum should be like D of some function. And actually the functions must also satisfy some compatibility condition on quadruple overlaps. So this sort of thing seems more complicated, but the net result anyways is that, the thing which is well defined is a D plus two form, which is the D of the C. Because I go from chart to chart, it's still well defined, but it's important to keep in mind that actually this closed two form comes from this locally defined, so D plus two form comes from locally defined D plus one forms, which themselves satisfy some conditions on double overlaps, which so forth define condition on triple overlaps. Because so by itself, a closed two form, well, just a closed D plus two form is just a closed D plus two form, but the collection of all this data is something better. It's what's called the Belinson-Delinka cycle, and physics call it D plus one form gauge field. And the point is that from this data, you can extract some class in integral cohomology, not just the Ram cohomology class. So whenever you have such datum, you can whenever this closed D plus two form comes from all this data, then you know that this cohomology class of this D plus two form is actually in the image of an integral class. So that's a good way to, that's one way to think about local description of integral cohomology classes, basically. And there's another way called Chigger-Simons differential character that I don't want to discuss it here. Okay. Anyway, so this viewpoint tells you that for in higher dimensions, actually we expect to get not a Berry connection, but more like a D plus one form gauge field, or this Belinson-Delinka cycle. And well, that's a subtle thing, but in any case, we expect that you should be able to define these closed D plus two form rather than closed two form. And by analogy with zero dimension, I might expect that maybe you can extract this class without knowing the details of the Hamiltonian, just knowing the family of the ground states. Kind of like a Chern class of a line bundle. Here's a little high Chern class of something. And well, this class is possibly quantized. Maybe you need put some additional constraint on your family of states. Like if you literally expect this Berlin-Sonderling cycle, then it will be quantized, but I'm not sure yet under what conditions it's true. Okay. Now let's now that we know what to expect, let's try to get it. Go back to quantum lattice systems and try to analyze this issue. So how do we analyze lattice systems? Well, there's this pretty standard apparatus called the quantum statistical mechanics, which is based on operator algebras. Now that involves some analysis, but luckily we won't need very much analysis. It's a pretty basic one. And in then one can everything. There's some nice piece of algebra which comes out of this analysis. So, but before, okay, so to see why algebra appears and what sort of analysis we need, let's forget about Berry phase for a second. Well, actually, for a few, for the next half an hour or so, I guess, or maybe next 20 minutes, 20 minutes, say, and talk about something rather different. So what's think about conservation laws in the lattice, because it turns out that these issues are like intimately connected. So if you remember, like in quantum field theory or even classical field theory, conservation symmetry by Noether theorem implies there is some conserved current, that is some vector valued thing which is conserved in this sense, if the equations of motion are satisfied, or on the quantum level, if the Heisenberg equations of motion are satisfied. Now, something which is not maybe emphasized in the elementary courses is that this current itself is highly ambiguous. You can add to it something like this, where H is skew-symmetric, and that doesn't change anything physical. So Noether theorem doesn't allow you to extract the current unambiguously. You always have some ambiguity. Maybe it's more comprehensible what this ambiguity means physically if you sort of separate this J mu into knot component, which is a charge density, and the spatial component with actual physical current. So this ambiguity, for example, says that if this H0I, these components tell you that the charge density itself actually is ambiguous. You can add some divergence of something. And it makes sense because usually you know what the total charge is. You know what the total charge is, but how what the density is maybe physically not so clear. Of course, if you like change, so Q doesn't change the total charge in some sense if you sort of drop the boundary terms, but the density is ambiguous. Also, even if you fix this ambiguity, there's still additional ambiguity in the current itself, because really the conservation equation divergence of this current enters. So like all such terms drop out anyway. So when you see expressions in the textbooks for currents, for example, you need to realize it's just some choice. Maybe in some cases there's some natural choices, but sometimes not so natural. Okay, what about the lattice setup? Well, that was all the continuum for classical field theory. On the continuum, we have some lattice, so like some subset of Euclidean space. Now, there's no time here. Time is continuous, but sort of the space has not been discretized to this lattice. As I already mentioned, you start always with an algebra of observables, which is a norm closure of some infinite product of matrix algebras. So this curly A, usually called algebra of quasi-local observables. And when you define evolution, well, you physically say you need a Hamiltonian, and mathematically, well, you mean what you need a derivation of the algebra. So physicists would write this derivation as a commutator of some Hamiltonian with the observable. But just keep in mind that this it's sort of a pictorial. It's this A is an observable. It's not an element in this curly A, but H is not an element in curly A. So it's not a really commutator of two elements in the algebra. Now, derivation just means that the usual properties satisfy this Leibniz rule. Now, in standard approach of statistical mechanics, it's always emphasized that, first of all, interesting derivations are not bounded. So the norm of this, if you have a control over a norm of A, it doesn't mean that you have control over a norm of this derivation of A. Second, as a result, is not defined everywhere on this norm closure. So it seems a bit strange because, physically, because, like to sort of differentiate any observable with respect to time. It turns out not every observable has a time derivative. What's worse is, typically you want to say that Hamiltonians or form a Lie algebra. If you commute to like Hamiltonians be the third one, but unbounded derivations don't conform to the algebra because they have different domains and intersection might be empty. So that's kind of not very convenient. But turns out, so this, if you look at it closely in the physics applications, nobody ever cares about these general unbounded derivations, and all physically interesting derivations have these very special forms. Like one way to write interesting derivations is like this. So maybe you have some sum over finite subsets of this lattice, and for each finite subset, you actually have an element of the algebra living on that subset. So that's, if you look at, say, some standard book on statistical mechanics, like Bratelli and Robinson monograph, that's how they set it up. So this is a kind of derivation which arises from physics. Any questions on this note? So here, these phi's are literally local observables, but the sum is infinite. This is well defined, sort of. Well, it's a reasonable derivation if this phi's of gamma are very small, if the diameter of this finite subset is very large. How small? Well, I mean, it should make a choice. Well, but also you can also might as well assume that the trace with observables is 0 because scalars don't contribute anyway to the commutator. And then minor normalization, they're anti-Hermitian rather than Hermitian. So extra factor of I compared to the usual normalization. Now, that's nice. Well, that's what people often use, but I don't like it because they're not uniquely defined, these guys, by derivation, and kind of hard to parameterize this ambiguity. And also, physically, it's more natural to write a bit differently. Write it instead of sum over finite subsets, write it as a sum over points in the lattice, where now I have commutators of observables now which are approximately localized in the sites. You can sort of reorganize the sum in this way, in many different ways. And again, each observable is now, again, it's a Hermitian, traceless, but now it's approximately, in some sense, localized near the point. So, and here is the first question: how do we parameterize ambiguity in this? Essentially, this f of p is a density of this derivation, as we discussed. Maybe you think of f as a Hamiltonian, and f of p is the density of energy. In other words, there should be some ambiguity in it. And the continuum and ambiguity is easy to describe. What's the analog of this ambiguity on the lattice? Well, first of all, what's the conservation equation? The conservation equation in the lattice is something like this. So time derivative of observable, say f, say suppose f is energy on some site j, should be equal to flux of energy from all other sides. So there should be some other operator, some other observable, or a sequence of them parameters labeled by 2 points in the lattice, which sort of flux current from j to k. And that's a conservation equation. So this sum is like analog of divergence in space. So each observer, well, these should be anti-Hermitian. Now, naturally, you want them to be skew-symmetric because flux or current from j to k should be minus the current from k to j. Plus, you probably don't want to, well, the sum better converge. So you want these guys to decay when j is far from k. And natural physical requirement that this, whatever this operator which describes current from j to k is sort of observable localized approximately at least near j and k. And the first question is, well, another question you can ask. So the first question is what's the ambiguity in the density of the derivation for a fixed derivation? Second one, well, given you decided on the choice of density of derivation, what is the ambiguity in the current, this JF? And okay, so and one can actually just answer this right with like specify a bit more precisely what sort of derivations we're considering. So, and for this, let me introduce this notion of chains on a lattice. So if you have a Q chain is a function of Q+1 variables, Q+1 points on the lattice. Sort of generalization of this notion of a current or so density is a function of a single lattice site. Current is a function of 2 lattice sites. Might as well generalize arbitrary number of lattice sites. It's symmetric, traceless, and localized on a ball of some radius, centered at any one of these guys. So plus, and also bounded. That's a nice condition. So I call these things UL, or uniformly local chains. So basically, each of these guys is non-zero only when the points J0 to GQ are not very far from each other, fixed by this radius R. But R can be arbitrary, don't fix it. Now, then there's a notion of divergence, which just summing over this one index. And that gives you a well-defined map from Q chains to Q-1 chain, which obviously squares to 0 because of skew symmetry. So this kind of, if you look at numerical chain, that will be something very rather familiar in the theory of metric spaces. They're usually called the resulting sort of complex is called the Viatoris-Rips complex, and people who like work on data analysis like this complex. But I'm working with similar thing, but the coefficients are not numbers, but these observables. So why is it useful? Well, because, for example, we can write this conservation equation without indices using this notion of chains. For example, density of a derivation or energy or charge, whatever, is a 0 chain, and current is a 1 chain, and then you can write conservation equation like this without any indices. So derivation acting on F is a divergence of the current. And now it's a bit clearer what there's some obvious ambiguities. If you even fix F and change J like this by del M, where M is some 2 chain, clearly that doesn't change conservation equation. Turns out there are no other ambiguities, and in fact, there's a theorem more generally which says that homology of this complex of UL chains is trivial for degree greater than 0. So anything closed is automatically exact if in degree greater than 0. And if you look at degree 0, this is just sort of finite range derivations, like finite range Hamiltonians or whatever. So for this reason, it's convenient. Well, you can make it more nicer if you sort of augment this complex. We'll change another thing with this nice derivations of finite range, because then the homology is literally 0 everywhere, no degrees. Okay. So they call it uniformly local Noether complex because it contains everything. Like here in degree 0, sorry, in degree -1, you have derivations, that is things like conserved quantities. In degree 0, you have densities of conserved quantities in a lattice. In degree 1, you have currents of conserved quantities. So there's everything in there. So, well, high degrees are not really very physical, as far as I know, but at least the lowest 3 degrees are all have physical interpretation. And yeah, questions?
Yeah. So in the continuum, is this also true? Like that the only ambiguity?
Yeah, in the continuum, just Poincaré lemma takes care of that, basically.
Even if you work on like some non-trivial space or something.
Yeah, it's still the same. No, it doesn't. Yeah, it doesn't matter because local coefficients with local observables. It's still true. The classical field theory that can. So, like, if you your expressions that you use not just a functional space, actual local functions of local fields, classical fields, and still within that complex, I think homology is trivial. Okay, so one can actually modify the setup for our purpose. More useful complexes where like chart, your derivations, not like, so where your chains are not literally localized, but approximately localized at some sites. So what I mean is that observable living on, say, for if you pick some Q+1 tuple of points, then it's approximately localized in some way near these points rather than the tails, which decay very fast. But still, all the summations over sites converge very rapidly, and then you can still get del squared 0. And you can define again derivations, nice derivations, when uniformly almost local derivations, the one where you have a sum like this, where A's of J's are not local or finite radius, well, not like finite radius, but just have tails which decay rapidly. So basically corresponds to Hamiltonians with rapidly decaying interactions. and this this notion of rapidly to make it to formalize, you can actually so these derivations, they're not well defined on the whole quasi-algebra of quasi-local observables, but they're well defined on this very particular dense subalgebra, namely these observables with controllable tails, namely which are local to a very good approximation. So quasi-local observables just some horrible things which have tails arbitrarily slowly decaying, pretty much. But this almost local observables are one which have rapid decay, like say faster than a polynomial. And it's sort of canonical subalgebra because local algebra, and it's a crucial kind of thing that you can choose a subalgebra and just work on derivation defined everywhere in the subalgebra. And then, nice derivation have this form by definition and preserve the subalgebra. And then, and the theorem says, another theorem says that, the homology of this chain complex of nice derivations augmented with these chains is still trivial. Meaning if you live in the world of these almost local observables and almost local these derivations, nice chains, all the ambiguities in the choice of, like, say, density of a conserved quantity are the obvious one. There's nothing funny going on. And by the way, that's a very useful technical result because, for studying, say, physical questions like transport of energy on the lattice or something.
So I thought you said that the derivations were unbounded.
They're unbounded if you look, but they're not defined ever on the quasi-local observables, but defined on this dense. The only derivations we consider are defined everywhere in this dense subalgebra, moreover preserving this dense subalgebra.
Okay.
Yeah. Now, technically, what this really means that you can set up all the definitions so that this almost local observables and all these chains and almost local chains and nice derivations, they're all nice topological vector spaces, so-called Fréchet spaces. And these chain maps are all continuous in this topology. So, another thing, I'm labeling everything by this degree, which is kind of funny. It labels runs from -1 to +infinity. It's not just historically so happens because zero chains depend on one point in the lattice, so -1 chains depend on no points. But of course, the more natural thing would just shift this grading by 1, so that things start with 0. And I'll maybe later do that. Okay, so now, so this is these are useful technical theorems because they tell you right away that any local symmetry or local Hamiltonian has some local current, for example. That's something which is sort of taken for granted in physics literature. But if you, like, say, ask, okay, what is the density of energy in the lattice models? For some reason, textbooks like kind of skirt this issue. But in reality, there's a very simple sort of answer. This is the formula for the energy current. If you have a density of Hamiltonian on site K, this is HK, then the current is the object with 2 indices. In fact, in a textbook, on condensed matter physics, you won't even find a definition of what I mean by current in the lattice. So again, they skirt this question, but I actually learned about this formalism from Kitaev's paper on anyons and exactly solved model, that the current in the lattice is a thing with 2 indices. And that makes everything very clear. It makes clear that that's how you get the energy current. Now, this energy current, of course, is ambiguous. You can always add something exact to it, but this is sort of a canonical expression, nevertheless. Now, you can ask, okay, what is this? Since this commutator occurs, it's a nice way to construct a guy with 2 indices out of a guy with a 1 index. So, more generally, if you have 2 zero chains, densities of some conserved quantities, you can form this bracket, which is it's not a Lie bracket because it takes you from these guys to something with more indices. So it's this bracket of degree 1. So from 2 guys of degree 0, it gets to degree +1. Now, how does this fit into the story? What is it doing here? And here, by the way, that's where things deviate from the field theory, because in field theory, there's nothing similar. So it turns out that this actually extends to the whole chain complex. So there is a bracket of degree +1. You have 2 chains, P chain and Q chain. You can just define a P plus Q plus 1 chain by this sort of obvious formula. Just take commutators and skew symmetrize. So as there is, this satisfies Leibniz rule with respect to this del. So the whole thing is what's called differential graded Lie algebra. Well, it's kind of shifted because of this +1. It's a bit, I should have shifted degrees by 1, so that things start with 0, not from -1. If I did, I just get normal differential graded Lie algebra with the bracket of degree 0, but here it's degree +1. So, so it means that there's a graded Jacobi and there's graded Leibniz rule. And the special cases of this is, for example, if you look at the degree -1, guys, this is just the usual Lie bracket of derivations. And again, for unbounded derivation, there's no Lie bracket because you have problems with the domain of definition. But for these nice derivations, there's no problem, and you get the Lie bracket. So as for them, and that's Q-symmetric guy. And for the 0 chains, you get a bracket which takes you to 1 chains and sort of to currents. And that operation is symmetric, actually. It's symmetric because it's a graded Lie bracket, and then after you shift the grading, the 0 chain is actually fermionic objects, so the bracket is actually symmetric rather than symmetric. Well, derivations are bosonic objects. So, okay. So this has some, and I'm going to comment on the relation with quantum field theory, but in quantum field theory, there's nothing exactly, well, it does work so nicely. So one can sort of make a little dictionary for the quantum field theory to lattice. So in lattice models, for example, 0 chains, which represent charge densities, but in quantum field theory, you use d-forms if you're in d+1 space-time dimension. So it's a charge density, say it's a d-form because you can integrate over the whole space and get a charge, which is a scalar. A current, well, in lattice, it's a 1 chain, as I mentioned, so it has 2 indices. But in the continuum, well, physicists usually write it as a vector, but it's better to dualize it, like Hodge dual, and say it's a d-1 form, because then conservation equation will just d over the d-1 form. So in general, p form corresponds to d-p chain. The Ram differential corresponds to this chain differential on the lattice. As I said, the bracket on the lattice doesn't have a good counterpart on the continuum. Well, you can integrate forms over submanifolds. Okay, the corresponding, should be some corresponding operation of construction of a chain with something, and I'll discuss later what it is. Yeah.
So in field theory, we'll typically talk about currents for currents of continuous symmetries, but on the lattice, it looks like there's no.
It's all for continuous symmetries only still.
It's only for, so where in the lattice do you restrict to?
No, just by definition, you can only have you can generate a symmetry. You can only generate continuous symmetry by derivation, right? I only consider continuous symmetries. Yeah. For discrete symmetry, there are no currents. Okay, so now I'm not entirely sure what this formalism is good for, apart from this clarifying the issue of what are the currents and what the ambiguities in the currents. But say higher forms, okay, maybe I have some extra ideas how to use it, but where it's really useful is some related problem. So let's well, so far everything was just pure kinematics. I didn't have any states, just in the kinematics of lattice models. But let's look at the dynamics. So dynamics means we have also a Hamiltonian maybe somewhere. It has a ground state, which is some positive linear function on your algebra. Okay, then here's a key notion. You say an observable does not excite the state if the average of the commutator with any other observable is 0. So, like in a finite dimensional case, it's equivalent to saying that if your algebra was finite dimensional matrix algebra, and the state was just a vector state in this algebra, then it's the same as saying that your observable A, that your vector representing the state is actually eigenvector of this observable A. But nice thing about this, I don't have to think about Hilbert space. It's just purely in terms of this C-star algebra. Now, it seems like there are not very many such observables. It is not obvious how to construct any if somebody hands you a state, but actually there are plenty of those. We'll see in a second how to construct those. Well, for some particular states. Well, similarly, derivations, it doesn't excite the state if you have this kind of condition. Again, that is more familiar to physicists because that's kind of thing you say when you say that your symmetry corresponding to derivation is not spontaneously broken. So if your F is just a charge operator, then this is precisely what it means for a symmetry for the state omega not to break U1 spontaneously. So like the better books on quantum field theory explain this, but most books say that spontaneous symmetry breaking is when, most books say that if you have symmetry is not spontaneously broken, then the charge acting on the ground state gives you zero. But that's not the right way to do it. This is the right way to formulate. First of all, because derivations typically don't become operators on your Hilbert space. It doesn't make any sense to act with the derivation on the state, but this makes sense. And similarly, for a Q chain, you can define notion of a Q chain which doesn't break, doesn't excite this ground state simply by saying it's commutator with any local observable component-wise thing for observables. That's a bit more harder to explain, but the point is, okay, so if you look at the reason to define it, first of all, if you look at subspace of all chains and derivations do not excite some particular state, then it's easy to see that first of all, they form a subcomplex, and second, actually, even a subalgebra. Like, so you have this Lie algebra, differential graded Lie algebra of all chains, but then there's a subalgebra, which of those don't excite the ground state, or this state omega, for any state omega. And the important result is that actually, if you have a gapped ground state, then this subcomplex still has trivial homology. So that's rather non-trivial. Yes. Is it just going to be the chains that need values? So chains are general chains without the subscript omega. They're just functions, symmetric functions of Q+1 points in the lattice with some decay conditions when the points are far from each other. Right, so you're just asking with the values of those functions. Yeah, these functions must be not excite the ground state. So somewhat magically, it turns out that this subcomplex for a gap ground state. So here's important: there's a gap. The state itself is a ground state of some local Hamiltonian. It's a non-trivial result that this complex still has trivial homology. Well, yeah. So I'm not going to show the proof, but a special case of this. This is a generalization of some result which are going to be found in Kitaev's paper, one of the appendices of Kitaev's paper. Namely, it was about essentially degree zero case of this theorem. To look at degree zero. So if you look at, say, a Hamiltonian of any system, by definition, Hamiltonian doesn't excite its own ground state. So now I can ask, okay, can I write a Hamiltonian as a sum of local terms, as a del of some zero chain, so that every term in the zero chain doesn't excite the ground state? So that's a statement about triviality of homology in degree -1, I guess. It turns out that's true, and Kitaev showed this. I'm not going to show how, but here's let me just say it again what he showed. He says that so suppose, or if your H doesn't excite the ground state by definition of its own ground state. So can we find like some way of writing this derivation in a different way okay, each derivation comes from a zero chain. But can write, there's lots of ambiguity. Can one find another zero chain which still produces the same derivation but does not excite the ground state? And that turns out to be possible if this ground state is gapped. That's what Kitaev showed, and that's fairly easy if you know Lieb-Robinson bounds. But I'm not going to get into this. And this theorem I stated here is just a simple generalization of that. Okay.
I thought there was this problem that the Hilbert space changes as you go through the point or something.
Yeah, I never use the Hilbert space. Yeah, I never use the Hilbert space.
Oh, but you use the state, but I thought those.
Yeah, I use a state. You could extract a GNS representation out of any particular state, but I'm not using it. That's yeah. As I say, there's very little analysis is used here. I don't even use GNS representation really, except in this. Okay, in this Kitaev theorem and this generalization, GNS representation is used, but that's about the only place where it's used. So I never actually work with operators in the Hilbert space. So I work with only with observables. It makes actually my life much easier. Anyway, so there's another application of this. So anyway, so here's finally how to get the high Berry classes from a lattice system. So first of all, we need a definition of what I even mean by a family of many-body states. So here I recall that the space of derivations, of nice derivations, actually nice topological vector space. And so it makes sense to say that, say, one form, if I'm M, I consider one forms with values in this space of in these derivations. It's a smooth one form. I want to say that I have a smooth family of states if there's a family of states parameterized by some point in this manifold, which is currently constant, sort of with respect to the connection of this sort. Okay, so globally defined connection one form. So what it means is that if I take an average of any observable with respect to this family of states, I get the actual function on manifold M, and the exterior derivative is given by this. Or slightly more generally, suppose I have not just a well, okay, here A is like this almost local observable, not always a local one, because otherwise this is not even well defined. So more generally, if I have a smooth function on the manifold with values in this almost local observables, I can I demand this. So somehow when you move D under the averaging, it turns into covariant derivative with respect to this connection G. Like if you think about, say, what is a covariantly constant, how to define covariantly constant things in a finite dimensional vector bond, that's how you define them. So this is identity. So there's some motivation for why I define families in this way, but I'm not going to get into this. So this immediately tells you something. So just because D squared is 0, that means that average of f of A for any A, where f is the curvature of this connection, is actually 0. That, of course, just means, another word to say it is this two form. It's obviously a two form with the values in derivation, but actually it's in the subcomplex. It's preserved. It does not excite the ground state, simply because of this identity. 0 is equal to, after averaging it's 0. And of course, well, another thing more obvious is that it has the Bianchi identity. It's currently constant. That's the usual standard thing. Okay, so we have this our seed for everything that follows. For every family of states, which is or some manifold M, you can assign to it some two form, which is first of all doesn't excite the ground state, this family of states pointwise, and second is currently constant. So what does it bias? Well, it turns out actually bias quite a lot. Okay, here's a little bit of motivation. Turns out you have a family of smooth family of local Hamiltonians with unique ground state, such that all these expectation values are smooth functions. Then this one form exists. It's a result of Ogata and Moon. So just motivation. Okay. So now I can finally define this Berry class. Well, I use it. There is this closed two form, not closed, covariantly closed two form F. Let's start with actually is it equals 0. I can define the usual Berry curvature in this way. Well, in 0 dimensions, this nice derivation algebra of derivation is just algebra of matrices, algebra of endomorphism of my finite dimensional Hilbert space. So it makes sense to average it over my space. Okay, so after I average that, that's closed, right? Because D of this thing is 0. Right? Okay, so that's the usual definition of that's the definition of the usual Berry class. By the way, notice I managed to define. Usually, when people define Berry class, they say, "Well, consider a line bundle, blah blah blah, over parameter space." Here, I never mentioned line bundles. In fact, I never even mentioned the Hilbert space. So all I used is the family. I have a fixed algebra and have a family of states, and extracted and the covariantly constant respect to this connection G, and extracted my Berry class. That gives us hope we can do the same thing for the case of many body systems where actually I don't have a nice one fixed Hilbert space. Okay, so how does it work? Okay, so now if you're greater than 0, you cannot actually take average of this two form because it takes value in some derivations, right? And derivations don't have averages in higher dimensions. Say derivation is like a charge, and charge is infinite sum of observables, and infinite sums don't have averages. It's a formal sum, right? So that's what I say here actually. So the derivation is something like this, which each of the each of the observables is approximately localized, so I can take average of each of them, but if I take the sum, I'm going to get infinite. That's just a statement that the usual Berry curvature, if you try to define it, is actually infinite. So it has a divergence as the volume goes to infinite. And that's another sort of more physical way of explaining why this niceties about GNS representation, whether they're equivalent or not, different points, why they actually have physical meaning. Because otherwise, you know, that's a physical way of saying what's the problem with the usual Berry curvature. Okay, what do you do instead? Well, like remember we have this differential graded Lie algebra. Maybe we shift the maybe we shift the degree so that bracket has degree 0, degree start with 0. But then for any differential graded Lie algebra, there's a notion of a more Cartan element. It's something which leaves some element of degree 1 which satisfies this equation. Now, in our case, we consider the following differential graded Lie algebra. Well, it's nice derivation, and the rest is this chains not exciting the state. So I want to construct what's the more Cartan element. So now in the bracket, well, the differential just a differential combination of a differential. Okay, so my complex is forms with values in this guy. So total degree is a form degree plus degree of this complex chain complex. Say yeah. So for example, G itself, this guy, it has degree 1 because it's first of all a derivation. Second, it's a 1 form. Derivation is placed in degree 0, so total degree is just 1. Now, however, it's not a more Cartan element by itself because this expression, if you just replace this red G with this G, you're not going to get 0. You're going to get that curvature 2 form F. It's not a more Cartan element. But you can now try to actually complete this to a more Cartan element, right? So by adding some things which have higher chain degree and higher form degree, so that the total degree is actually still 1. So now, and standard result actually that when the homology of your algebra is trivial greater than 0, you can always solve all this equation and complete your seed, which is this guy, to solution of more Cartan equation. So you can see it directly. So here's a sequence of equations, like the first one, say. So what do we have here? Well, first one you have an equation like that. Why does it imply? Why can you solve it? Well, F sits in degree 0, lowest degree. So of course, its del is 0. There's nowhere to go. So it must be del of something else by this, if you have a trivial homology. And second, like way, so you can solve the first equation. Now it's a 2 chain. Sorry, it's a 0 chain with values in 2 forms. And next stage, you have to solve this equation. Why can it be solved? Well, it can be solved because if I hit this first term here with del, we're going to get 0 from the and then if everything closes exact, so you can solve this one and so forth. So at every stage, you can check that the things you're trying to solve for this next guy using the previous guys, and the previous guys, they'll close, therefore solution exists. So all you know is this. You know. Okay, so we can all solve this, and now what do we do with this whole thing? Well, we need to extract some observable out of this form valued chain and take some average. Okay, so here we need to integrate chains. I don't want to, you know, how do I assign observable to a chain? So let's just do one chain. So let's go for one-dimensional systems. You can essentially work with one chains. So one chain is a guy with two indices. How do you integrate a guy with two indices? Well, you can, for example, split your one chain into two parts and do the summation. So one index is to the left of the cut, the second is to the right of the cut. And that I call it integration over something. So consider if you think about this H as a current, this is like flux of this current through a section. Kind of makes sense, right? So remember, H PQ is a sort of current from Q to P, right? So I sum all currents from to the left, points to the left to the parts of the right. So just a flux of a current. Now, it's kind of funny procedure, but the main point of this is that the main property of this is that integral over something exact is always, if your H is itself del of some two chain, then you get zero, actually, easy to check. It's kind of Stokes theorem. So that's the main motivation for defining this way. And now I can show how, at least in the dimension one, how to construct some. Well, what do we expect? We expect to get a closed D+2 form for a D-dimensional system. So in particular, for one-dimensional system, I expect a closed 3 form. Let me try to define it. So I have a 3 form already, this G3, but it's a 3 form with values in one chains. So what do I do with it? Well, first of all, I take average. Sorry, I should put it. I should probably change the order. I should really first integrate and then take the average. So integration gives me an actual observable, and then I take average, you get an actual number. So you get a numerical 3 form in this way. Now, why is it closed? Well, that's a trivial manipulation, because now if you take a d of this, then you move little d is equal to covariant d, but covariant d by this Moore-Cartan equation is del, and then by this property here, you get 0. So it's a closed form. And also can show that this, the next Moore-Cartan equation tells you that actually this result, that this 3 form, well, depends on where you put the section, but the cohomology class doesn't depend on where you put the section. So this gives you a well-defined cohomology class. And then, well, in general dimensions, you do something similar. So in general dimension, you need how to integrate, well, if you're in D dimension, integrate a D chain. So how do you do that? Well, choose some D+1 conical regions in your RD. Say in 2 dimensions, you like split your plane into like 3 sectors. These lines don't have to be straight lines, just some lines which go off to infinity. Integration is simply the sum like this. So each index runs its own region. So again, Stokes theorem holds, you can check, and then if you integrate and take average, you're going to get an actual numerical D+2 form. And then the same kind of argument shows it's closed. Now, all of these things, of course, seem a bit arbitrary because, well, we solved Moore-Cartan equation first, but the solution, of course, is highly ambiguous. But in the end, turns out, even though, of course, the form depends on the choice of the solution, but the cohomology class doesn't. It's actually a topological invariant of the family in that sense. So, lots of ambiguities in this whole business, but in the end, the cohomology class is unambiguous. Okay. So let me just finish with some remarks about quantization of this thing. First of all, we don't expect this cohomology class to be quantized in general, but for one-dimensional system, we can show that it's quantized. Well, for invertible one-dimensional system, to be precise, but everybody believes it in one dimensions, all gap systems are invertible. Also, another remark is that that in the usual Berry phase business, the actual two form it has a physical meaning, but here I don't know how to define actual two form. Our two form is closed, but it depends on various choices, which are not very physical. So the best one can do, it seems like, is the cohomology class. And the third is also one can generalize to the case of a G equivariant family where G is some compact Lie group. So you have some action of the group on the manifold, which preserves a state. Then one can attach to this family element of the equivariant cohomology group of M. And that's actually interesting even for a point. That is for a single state invariant under element action of the group G, because you get then, well, equivariant cohomology of a point is simply G invariant polynomials on the Lie algebra of G. And this same thing is classified like Chern-Simons actions for group G, and then so for G invariant state you get some Chern-Simons, natural Chern-Simons form. So that's an interesting way to recover things like Hall conductance and Mendelian analogs directly from a state of a system invariant under some compact Lie group G. So I guess I'll stop here. Yeah.
Let me 1 second. Yeah. I need to, yeah. Thank you very much, Anton, for the nice talk. Are there questions? Yeah. Let's do it this way. I mute and maybe you unmute.
So is there a straightforward way of extracting G from, say you're given the family of states and get G, or given a family of Hamiltonians, you can extract G?
So if you have what, sorry?
But if someone gives me like a family of states, is it easy for me to extract this G?
No, I mean, well, what is a family of states itself? I mean, you need to define what you mean by family of states.
I guess like a state for every point in my manifold.
No, it should be some notion of smoothness. Should be some way to say that the points nearby and somehow states nearby in some way smoothly connected. So there are other ways to define what I mean by a family of states, not necessarily using this G. And then you can extract G from those data, but you cannot just arbitrary family of states. You need some.
But given like a Hamiltonian.
Yeah, if you have a family of nice family of Hamiltonians, I think one can extract this G, but in practice, it has only been shown for a family of local Hamiltonians, finite range Hamiltonians. This paper of Ogata and Moon, which I like flashed in one of the slides, shows that if you have a family, smooth family of finite range Hamiltonians, and the gap ground state for every members of the family, then you get this G, and therefore a smooth family of states. That can probably be generalized. It should be generalized to more general families of Hamiltonians.
A local Hamiltonian is fine.
Well, finite range doesn't seem very natural because in this whole business, like Hamiltonians with decaying tails should be okay, and then, but their argument seems to use their finite range.
This condition of smoothness for family of states. But so if this is a generalized cohomology theory, there should be like a topological notion, right, of phases characterized by homological space X. Do you have any idea on how to like get any? Yeah, have you ever thought about trying to get rid of the geometries?
Yeah, well, I'm not sure it's possible. Well, I don't know how to get rid of geometry, but it seems to me that some, maybe topological, in the end, we want to extract maybe topological space of all states with some nice properties, but maybe only want to extract the homotopy type. And maybe that's a better thing to look for. And then you don't need topology a priori.
You don't think that there should be like a notion of like a continuous family of states over space like that?
Maybe, but it seems to me that it's not very natural to start there. Maybe, well, one can get a topology in some roundabout way, for example. Maybe you want to define your space of states, maybe the simplicial set, and then get topology from geometricalization. That simplicial set. So it doesn't seem like there's a very natural notion of topology on the space of states in this business. Like the ones which come from C-star algebras, they're nice, but they don't seem to have any relevance to this problem at hand. Like there are all kinds of topology in spaces of states, but the ones which we consider don't seem to be relevant.
Yeah, further questions? I have one question concerning the Mauer cutoff form. And it seems that, I mean, in the whole deformation theory, a la Kontsevich, and actually goes back, I think, to Deligne and others, there is deformation is described by a differential graded Lie algebra. And the question, it looks kind of like your approach could be connected to that. Have you thought about that?
Well, formally, one can think of this differential graded Lie algebra as some sort of a resolution of the algebra. Okay, if you look at the Lie algebra of all derivations, modulo those which preserve our fixed state,
Yeah.
then you can think of the one I'm using as a resolution of that algebra. So, except I'm not sure how to make sense of this, because in the world of these topological vector spaces, quotients don't have very nice topology.
Yeah.
So it's some formal substitute. Yeah, so this, yeah. So the Lie algebra of so you would like to say that the space of all states is the group of nice automorphisms modulo the subgroup of those which preserve your, say, trivial state on some given state.
Mm-hmm.
Now, on the infinitesimal level, you would also say that your tangent space to this space, to the moduli space, is yeah, Lie algebra of this group of nice automorphisms by the subgroup which preserve the state. But it's kind of difficult to make sense of this. So on the form, yeah, we would like to think of that our differential Lie algebra is a tangent space. Is some replacement or resolution of this tangent space at a fixed point, but then I'm not sure how this makes sense.
Okay, thank you. Are there questions from the outside? No, then let's thank the speaker again. So thank you, and until next time.
Thank you. Thanks, Marcus. Thanks, speaker.